Morning. Thanks. Pleasure to be back here. I spend less time here than I either should or like, but we'll see if we can change that. The organizers of the meeting, I much thank for asking me to come. They handed me this title, Neutron Star Exteriors, which covers so many sins that, of course, I'm going to duck from a large fraction of it and stick to things that are a very active area at the present time, and I like to pretend I know something about. I didn't stick to their title, and I will not. You can see almost everybody knows where this title comes from, but I can't stand the idea of actually giving a proper attribution to the person who invented this cute line about known knowns, etc. So I won't name him, but you know who he is. The known knowns, of course, is anything in this kind of subject. In most cases, they're sort of known. A few are very known. I personally really like the rotation-powered pulsars. They are, besides being full of really fascinating phenomenology, they are our first example, and in some respects, foremost example of a Poynting flux-dominated relativistic outflow system, which over the course of time, the idea of being magnetically dominated in a relativistic outflow has become more and more widespread and popular, to the point that in these days, AGN jet people and GRB people mostly talk about Poynting flux-dominated systems. It's a big change from 20 years ago. The pulsar example has a great advantage. The rotating dipole has electromagnetic spin down, and going with that is a minimum amount of electric current that goes with it that has to be there. In contrast to the other systems that people talk about, in this case, because we do the exquisite information that comes from pulsar timing, and for this kind of field, the high certainty of what a neutron star moment of inertia is, which I think Andrew would probably quarrel with me that it's certain, but by my standards, it's certain. We know what the energy budget is. You measure period and period derivative and borrow a moment of inertia from the concordance equation of state calculations of the neutron star structure, and you know what the energy input is. None of this quarreling that goes on in the GRB or AGN jet world about what is the total amount of energy that we're dealing with. However, of course, this doesn't tell you much about how it partitions into various things. And that's much of the interest of working with the pulsar magnetosphere problem and the pulsar wind nebula problem. You can get a handle on some of these compositional and other kinds of issues, but which are full of astrophysical uncertainties. So I will try to give a spiel about that. One of the triumphs of the last decade, really 13 years, 14 years, has been something that was talked about starting in the early days of pulsars, where based on vacuum modeling, the energy loss rate is related to the magnetic moment of the star by this well-known formula which you can guesstimate immediately. The things that we don't know are the prefactors and dependence on other parameters neutron star, and this hasn't gone away. But in the early days, people also realized that the electric forces are such that it's unlikely to be a strictly vacuum problem. And the idea that there was charges extracted, put out into a magnetosphere, and would turn into some sort of wind flowing out, so that the problem gets, in a sense, turned into something like the spin down of the sun or other normal stars with a toroidally wound up field and a wind flowing out, was put into the people's consciousness early on, but it took a long time to get a solution, and I find the psychology of that history is fascinating, because the basic idea is the magnetic field is so strong that the system is force-free. Only the electromagnetic forces vanish. Only the EM forces matter. Pressure and inertia are unimportant. that leads to a very cute, especially for the aligned rotator case, single equation describing this, which appealed to all sorts of applied mathematics-minded people that, gee, this lovely partial differential equation, I must be able to solve it with pencil and paper. Time goes by, and there are all sorts of things that claim to be solutions which aren't put in the literature. And the reason is that the problem as presented is a nonlinear eigenvalue and eigenfunction problem, where the current that's flowing is an eigenfunction you have to determine by having the solution having characteristics which you believe to be true for stellar winds, namely it's smooth everywhere. And there are no analytic solutions to something with a rotating dipole never appeared. Finally, the modern age descended, and that gadget known as a computer, actually, the younger people who were not afraid of computers proceeded to do something about it. So the textbook answer is right there, and actually calculating the electromagnetic field around a vacuum, dipole rotating in vacuum is something that you'll find in Jackson. Depending on the age of the person writing the paper, they refer either to Jackson or Panofsky and Phillips. I'll leave you to guess about where the age cut up, which book was referred to by which category of people classified by age. The relativistic rotator with plasma that fills the whole magnetosphere, done in the force-free approximation, was first done by Spitkovsky in 2006 for the oblique rotator. It was done by Yannis Kantopoulos and friends in 1999 for the aligned rotator. And this innocent little formula right here, I left off a multiplier which expresses the uncertainties that come from the numerics, which in your first work is around 10%. I suspect things are somewhat better now, but it's, it looks like this. If you do the calculation, do the simulation for a variety of obliquities between the magnetic moment rotation axis, you get what the torque looks like, and you can fit it with this thing. And this innocent-looking formula is I regard it as one of the triumphs of computational astrophysics in the last decade. So this is an example of, to certainly a useful level, a known. Going with this rotating object, there's a voltage across the open field lines. The plasma-filled rotator has true open and closed field lines, something that people don't always appreciate, is the vacuum rotator has no open field lines. It has field lines that wind back an awful lot, but they then come back again. It's not an important issue, and the vacuum particles don't stick to field lines anyway, so it's not a significant issue in its own right. The open field line voltage, I have a rotating magnet. Faraday taught us if I rotate a magnet, I get a voltage. So the numbers are this kind of thing. And when I go and give talks about this stuff to the high current electron beam community, which hasn't happened in recent years but used to, they always get impressed with these things. It's somewhat larger than a high voltage Marx generator can deal with. But going with it in the model in which there's an outflow going with this, the open field lines have stuff flowing out. The original concept was this was a charge-separated medium, so you get a charge density moving along the open field lines. And this gives rise to a current. That current is still present, and its magnitude is the same as was originally guessed. It can be expressed in CGS-style electrical engineering language. I is equal to C phi. 1 over C is the resistivity in CGS units, and it's the resistivity of free space. Roger loves to quote this in MKSA units, I suppose because he has to teach physics undergraduates, or because he just likes to think that way. And it's 300 ohms. So the way I like to think of this is I got this rotating magnet which creates a voltage and is trying to drive a current against the impedance of free space. And this is the answer you get. These are the kinds of currents that flow in this type of thing. The ideal magnetosphere, the ideal MHD magnetosphere in force-free or non-force-free approximation has the usual assumption that the electric field along B is equal to 0. That means that the field lines have to co-rotate, and the electric field is then this well-known creature right here. Going with that is this charge density. numerically for a 1 second pulsar at the surface of the star, this corresponds to about 10 to the 11th elementary charges per cubic centimeter, and it goes up scaling with what you can see. There's a particle loss rate that goes with this. If I say it's a single charge is coming out, either electrons or protons, depending on which field lines you're on, you get a certain number loss rate, with the exception of one factor, because I is equal to C phi, just take one C away, you'll get the voltage back again. Numerically, this number here is around, for a 1 second pulsar, is about 10 to the 30th charges per second. For the Crab pulsar, it's around 10 to the 34. These are, in terms of theory, these things have been known for a long time. What's happened, of course, is that people have gone to an MHD kind of model. You start thinking about all the things that go into the structure of something that has closed and open field lines that we're familiar, a lot of which were familiar to us from geophysics. And so you're going to see some geophysics come back. It certainly haunts me. Whether it haunts you guys, I don't know, but in my opinion, it should. And a lot of what's driving this is the wonderful achievement of primarily Fermi, also Agile, at getting instead of a class of first 2 gamma ray pulsars, which is the 1970s, 3 is the 1980s, 6 is the 1990s, one of them a rather odd duck. Now we have, at last I noticed, around 135, and I'm sure still counting. I hope Roger will say more about that when he gets to it, but it's, or at least what he's allowed to say. In particular, you get to ask serious population synthesis questions. It used to be people who do population synthesis. Being astronomers, if you have two objects, you can do a population synthesis. If you have 3 objects, you can do it. But you're not learning a whole lot that way. Now we are. One of the known knowns is that in the early days of pulsar theorizing, the idea was that the polar regions have its current coming out, and it would behave like something like a space charge limited beam, accelerating all the way up to whatever voltage is allowed by the geometry and freely emitting charges. Or different kinds of models would say you couldn't extract anything at all because the crust had, the surface of the star was just a bare crust, and it had such a large binding energy you couldn't get any particles out. So that led to a vacuum over the surface. Either way, those ideas led to the idea there's a large voltage drop parallel to the surface, and you will accelerate particles to very high energy, and they'll radiate gamma rays because they're moving on curved field lines. And then all sorts of wonderful things happen, and I think they still happen, that the gamma rays you emit turn into pairs, and you get a pair plasma, which provides a much higher density than the charge density. But it also led to the thought that there would be gamma rays from the polar cap, and I actually got interested in pulsars at the time the first gamma ray pulsars were discovered, Crab and Vela by SAS2, that there was some way of looking at the pulsar using radiation which didn't have to come through the haze of getting the radio emission out. The radio emission depends on some sort of collective process. This is quite fascinating in terms of the plasma physics, but it's badly constrained to understand what it is you should even be thinking about, never mind getting a result which makes any sense. And I'll say a little about that at the very end. But producing gamma rays in the low altitude magnetic field is that magnetic field is very strong. And there's a well-known QED process of a photon, real photon colliding with a virtual photon that's is another way of stating there's a magnetic field there, leads to a strong absorption of the gamma ray and turns it into a pair. This has a sort of a guillotine-like opacity. As you pass optical depth unity, the opacity goes like the exponential of an exponential, and means there would be a really sharp cutoff to any spectrum there. One of the things that Fermi certainly did, I guess Agile did too, although I haven't looked at the papers closely, is that you don't see that super exponential cutoff. Instead, the energy, gamma rays roll off much more slowly. And as the ground-based gamma ray people have told us, at least for one pulsar, there's gamma rays coming out all the way up to 300 GeV, which means that to get them out through the magnetic field, you have to be at least 30 stellar radii off the surface. For the crab, that's more than a third. It's a third of the way to the light cylinder. So it's a long debate has, quote, been settled, unquote. It doesn't mean it's settled for every object, but it's in terms of the basic picture, it says we're getting this gamma ray emission from high altitude, nominally light cylinder emission. In the trade, it's been known as outer gap emission for a long time, but I will do my best to avoid this obnoxious word gap. One of the successes is to model the light curves here, and there's been a lot of focus on the beaming properties in the lighthouse picture. Namely, particles are moving along the rotating magnetic field, which is now this distorted dipole, turning into toroidally wound field outside the light cylinder, and trying to what you need to do in the kind of emission geometry that gives rise to this pulses here. Within the lighthouse concept, there's been quite a bit of success in doing that. I will say there's another concept of how to get pulses, which isn't so popular, but it's temporally modulated emission. And that's because if I wind up the magnetic field coming out from two opposite poles, out in the wind, it has this so-called stripe structure, which I forgot to put a picture in. But the field lines from one pole wind up, and the field lines of the other pole wind up, and they become like wound up spirals of oppositely directed fields separated by current sheets. And one model that has been talked about a bit is that you get radiation from this wind region with these current sheets, and because it's moving relativistically, the radiation from one current sheet doesn't overlap the radiation from another current sheet until you go a long way out. So if you let the emission go on for a little while and then shut it off before the radiation from one sheet overlaps another, you'll get pulses coming in on you. Recently, a number of us have written about this very casually over the years, and recently John Kirk has made a big campaign out of it. It would be, and it's possible to show you can get things that look like ordinary pulses. The details of these light profiles, nobody's tried to do it in that model, and I'm skeptical they'll get the right answer, but until somebody looks, you don't really know. What's important is there's a different predictions about the polarization of this stuff that you get from things. The basic model of the striped wind has oppositely directed sheets, and the current sheet, just the field goes through zero as you go through the sheet. There's no rotation of the magnetic field as you do that. So the field is just across the sky as you're looking at it, and it's first this way and then it's that way, but from polarization it doesn't matter. So you shouldn't see a rotating vector type behavior. Kirk gets around this by adding another component to the current sheet by hand. Okay. It would be lovely to have gamma ray polarimetry on this. Now I'll stick to this beaming model that we firmly believe in. This here is the current structure of the oblique rotator in a slice through of a 60-degree inclination example. And these are the features of gamma ray emission that traditionally are done, putting in by hand gap regions, semi-vacuum accelerators. The MHD model says no such thing exists, so I'm going to pass over that. The challenge is to construct a sheet accelerator in a high-density system. There's no vacuum around, which radiates enough gamma rays. And it's a challenge because here's this is from, I think, the second Fermi catalog, and you see this interesting behavior here of gamma ray luminosity as a function of E dot. There's a huge uncertainties here, and those mostly come from the distances. So it's the same old business. So if you can measure pulsar distances accurately, a lot of people would be a lot happier. There are always prospects of doing better on that. Another 70 parallaxes would be really cool. And the more they overlap with the Fermi catalog, the more I'm happy. Other people have different interests, but this business here of the luminosity, like the square root of the spin-down luminosity, which is loosely speaking in the data, is something that was discussed many years ago by Alice and by myself. That is, if you short out the accelerating voltage, whatever it is, with pairs, that tends to nail the accelerating voltage to a fixed constant. That means the luminosity, which is the current times that accelerating voltage, assuming it's radiation reaction limited, which it frequently is, then gives you the current goes like the square root of E dot, and the voltage of acceleration is a constant set by the opacity for gamma rays. So you get this interesting behavior sort of given by hand. It implies that within our accelerator we're getting some pair creation, which may or may not be true. I've got to make this move. Okay. So my take on this has been to try to pursue something we know from geophysics. If you have a magnetosphere and it's coupled to the outside world, so there's stress on it, and in the simplest case here, it's just the impedance of free space, you get a stressed magnetic field, which we know a lot about what happens to things like the Earth's magnetosphere. The stressed field lines, which are stressed by the solar wind in that case, have currents which map down to the polar regions, and in those polar regions, those currents can get very accelerated. So the aurora, which are this wonderful to actually look at, which in once in my life I've actually seen them in the sky, happened because there's an electron beam coming down from above, hitting the atmosphere and exciting the molecules in the atmosphere to give you air glow. So the radiation from aurora is not like radiation from pulsars. It's molecular radiation. But the acceleration problem is something that I think is similar. That is an acceleration of a particle beam along the polar field line. We know from those, experimentally, we get voltages that can be all the way up to and sometimes even larger than the voltage all across the magnetosphere. With no vacuum gaps at all. The density is enormous compared to this Goldreich-Julian density. And the reasons have, every plasma person knows perfectly well that you can get parallel electric fields under the right kinds of circumstances, usually in thin structures, that is, in twists of the magnetic field which have wavelengths across B that are sufficiently small that dissipation due to conductivity or viscosity or something plays a role in setting up a parallel electric field. So this is kind of the current structure down near the pole. There's current coming out in the middle, which is the main magnetosphere current. There's return current in a thin current sheet. The force-free models have told us there's also some distributed return current. The current system closes below the surface of the star down in the crust where at densities high enough that the collision rate is comparable to the cyclotron frequency. This is my personal pet cartoon of what's happening out of the last closed field line. You have closed field lines here, open field lines there. There's outflow from the polar cap regions. And as Yuri Lyabarsky pointed out now, getting close to 20 years ago, flow past this Y line right here is subject to reconnection. The current sheet likes to tear, and you set up reconnection. You get inflow from the wind going into this region here and also into regions out here. And that inflow then allows you to establish a return current going out here. The consequence is making this structure of the polar region is basically a standing Alfvén wave, species kinetic Alfvén wave, because the transverse wavelengths are small, and that allows you to have parallel currents and parallel electric fields. In the interest of time, I've got to keep moving. I'll just bounce over very quickly. If you try to model this kind of thing using the pictures of, starting with pictures of reconnection done by a variety of mostly 2D simulations. Once reconnection is set up, the current sheet, which was originally here, likes to break into so-called plasmoids and filaments of current here, and the accelerating electric field, the reconnection electric field likes to be along these X lines right there. If you go through this and say, well, what's the population of particles in this in the last closed field line region where particles can diffuse around freely by balancing the amount of inflow through the reconnection to exhaust coming out in the reconnection, doggone it, you get this little handy-dandy little formula applied to the crab where the numbers are kind of well known. The Goldreich-Julian density is like 10 to the 6th centimeter, and depending on the amount of pairs that are in the wind going by, That's important ratio known as the multiplicity. Right here, based on measurements of what the plasma content is of the pulsar wind nebula, in the case of the Crab, this number is at least 10 to the 6th, probably more, because the way you find it out, you're learning a lower limit. Pair creation theory likes to produce this kind of number right here. And one of the one of the known unknowns we have lying around here is how come stars know how to do this? Okay, I will just then slides and come to the end. You can do something about the temperature of the plasma in this region. It tends to be multi-GeV, but the luminosity is small because the volume is small, so you have to extend it out either along the field lines going inwards or the field lines going outwards, so as you get enough volume to radiate the gamma rays you're interested in. You can estimate the parallel voltage in this standing kinetic alphane wave. I get a number like this if I assume that this return current channel is surrounded by perfect conductors. That's probably not true. The simulation that Anatoly did recently of running an alphane wave pulse through a pair plasma with a strong magnetic field, and what you get is voltage likes this. You get an E-parallel likes to staircase up. That is, you're forming double layer-like structures everywhere. These are these kind of things here. And that's very familiar to the auroral physicists. That's what they actually see when they put a satellite up there. So I regard that as an encouraging extension of what we know. I'm not going to have time to go into this other than say there are many known unknowns. These are things I call, stuff about the gamma rays I call kind of known knowns, but many open questions of making models that actually work. One of the things I find quite fascinating is that the radio emission shows all sorts of long time scales to it. Pulses represent the rotation of the pulsar. That's the dynamical time scale of this electron light crossing time, alphane wave crossing time from surface to light. How come you get things like the pulsar can turn off for a month or longer and then come back again with the phase where it comes back is related to the phase where it turned off but isn't the same? During the off time and the on time, the torque changes back and forth. What happened there? So there are lots of ideas about this. My pet one, which I was going to show you in more detail, but I won't have time to explain, is based on this picture right here. Current comes down and in a thin structure like this, if you put the current into the crust in a thin structure like that, the resistivity is significant. And you can show that because the resistivity is degenerate, as the temperature goes up, the resistivity goes up. It's the opposite of a gaseous plasma. So you can find out that there is actually an instability there. It's a thermal instability, and the resistivity will run away. An interesting thought is that this is a toy estimate of the growth rate, which if the current sheet is thin enough, it can be down in the weeks to month range. A toy thought is, because if you put a resistor into a circuit like this in a high inductance system, you stop the current flowing here, but it's got to go somewhere else. So the current has to shift to some other set of field lines, I will get a change in the beaming patterns of the radiation. Is that what's behind mode changing? This is not an explored area, so I call this a known unknown. It's something that is worth pursuing. The most long-lived known unknown is the radio emission itself. And I will only make a shameless plug that it turns out this polar cap emission of pairs has to go through a discharge-like phenomenon, which done electrostatically, the spectrum of the electrostatic waves looks very like the spectrum of radio emission. So an undone, but both Timofey is working on it and Belobaradov is working on it, and Belobaradov is getting ahead of time. Timofey's getting worried that he's going to get overrun by a different machine. And so there'll be an answer to this. If you do this electromagnetically, it's almost certainly a direct electromagnetic emitter of stuff right in the radio frequencies. So it's an interesting piece of unknowns. I don't know what one can say about unknowns. other than high confidence prediction that pulsar magnetospheres and other neutron star magnetospheres are surprising us. So let me quit there.
The Aurora model, I guess you've got the return current basically being the source of the gamma ray emission now in a thin kind of return current region.
It's, to the extent that one needs really a thin sheet of emission, the thin sheet component of the return current is the most obvious candidate.
So those have to be particles flowing out.
Right.
If okay, so somehow
there's particles both flowing down and flowing out.
What
you get from the Y-line region is a downward particle beam, depending on what was the primary current. It's either electrons or positrons. And if you have downward electrons, then you induce the upflow of ions. So you can get ions, heavy ions fly out of the wind at the Goldreich-Julian rate.
But only from the Y point. So there really is.
They'll get into the wind in this reconnection region.
Yeah. Okay. So all the emissions coming from pretty much outside the light cylinder. In that
I think it can be. It actually spreads through there. That is as far as I can tell in this model, as it's developed to this point, is most of this voltage is delivered up near the light cylinder.
Yeah. Okay.
And nothing that says it has to stop at the light cylinder. It will go onward. The beams go onwards.
Sure.
And it'll
can go outside that,
onwards.
but not. Okay.
There's another variation of reconnection out at the Y line, which says that you're getting instead reconnection distributed beyond the light cylinder, and that's doing the radiating. That could well be true also.